All right, so if you take a look at the warm-up for today, where do we start on this one? We said yesterday there's the one thing that we're talking about was we know how to find now. We basically took the triangle sum and expanded it to quadrilaterals and pentagons, and now I can figure out the sum of any shape. So that's where we start. Okay, in this case, we're dealing with a pentagon. What's the sum of a pentagon? The 5 angles of any pentagon? 540. Okay, which you may have memorized already. Okay, which is perfectly fine. You may have to go back, but ultimately, that's where what we talked about. That's where that formula came from yesterday on our toolkit. The 180 is 180 degrees per triangle when we break this up, times n minus 2, n is the number of sides. Okay, and n minus 2, if you remember that, if we were to break this into triangles, we would end up with 3 triangles. That's what the parentheses is representing, how many triangles you have. So if you do that, that's where the 540 is coming from. That's how we can now use this this formula, if you will, and this idea to find the sum of any shape. So we know the total of those 5 are 540, and here's where the algebra starts to come into play. Okay, we add up all 5 of those angles. If we do the algebra, what do we get? 10, 12, 14, 16x plus 12. So if you add those 5 angles up, you get 16x plus 12. And we know, based off of what we said yesterday, that those should add up to 540 degrees total. Okay, and now the rest is do the algebra, solve for x. So in this case, subtract 12. You get 16x equal to 528. Divide both sides by 16, and we end up with x equal to, what is it, 33? Okay, yeah. 33. And there's what you should end up with right there, x equal to 33. Okay, again, whole concept of this, you could not do this problem before yesterday because you needed to know that those 5 angles added up to 540. Okay, and that was that main idea. Anybody have any questions on the warm-up? Anything not make sense? A couple of quick reminders while I'm thinking about it. Those people that you were not here yesterday, I did record the lesson. It's out there. So if you want to kind of go through and listen to the lesson of what we did to get to this so it makes more sense, go out to Canvas. It's in modules. Just click on the 812 lesson video. Other reminder, if anybody's coming in to take a test for me in this class tomorrow, I don't think anybody is, but just in case I'm forgetting, I won't actually be here tomorrow. So if somebody's coming in, remember I put in there, you're going to Mr. Notsky's room, 2 rooms down, okay? Because I will not be here. So just a reminder. Okay, let's go to the practice to learn packet. 2 things I wanted to mention. One problem I want to do together, and one I just wanted to kind of give you a quick heads up. So this assignment, the 812 assignment, is due by tomorrow. Okay, so you still have plenty of time to get this done. You're always going to have 2 days to do an assignment. Okay, so since we did 812 yesterday, always do 2 days later. It's due by Friday. Okay, we're going to do 813 today. We'll probably finish it up on Monday. So it won't actually be due until either Monday or Tuesday. I don't remember what I put on there. Okay, but you're going to have some work time in class probably on Monday as well. The 817 is the first one I wanted to mention real quickly because this is just a continuation of what we were doing in chapter 7, where it's the coordinate geometry. And the reason I bring this up is there's been some people that have turned this assignment in already, which is great. Okay, but some people have done a really, really good job, and some people haven't done much at all. Okay, and that's what I wanted to just quickly address as people are working on this assignment. Notice they tell you to graph the 3 points, which will create a triangle. And then the question right here, 2 things. What is the most specific name for this triangle? Anytime you see those types of directions, what they're really asking you is, if we're talking about a triangle, they want you to name it based on the side lengths. Okay, so is it scalene, is it isosceles, or is it equilateral? And they want you to name it based on the angle measures. Is it acute, right, or obtuse? Okay, so your final answer for part A should end up being something like a scalene acute triangle. okay? Or an isosceles right triangle, something like that, okay? You should be very, very specific. And then here's the part that's, I was a little bit surprised, and that's why I'm addressing it right now. Some of the people that have been turning this in are completely skipping this part right here, using both the slope and the side lengths. This is exactly what we were doing in chapter 7. Find all the slopes. In this case, you should have 3 slopes and you should have 3 side lengths. Then, based on the slopes and the side lengths, you should be able to answer that question. Okay? You should know what the what kind of angles you've got. You should know what kind of side lengths you have. You should be able to answer that. So make sure you do both of those, because if you just put an answer down, like I think somebody just randomly put down, you know, just an answer with no work whatsoever, just an answer to the problem, and that's not even close to being good enough. Okay, you got to do the work. The work tells you the answer. Okay. All right. So that one, I just wanted to give you a quick heads up on kind of what the expectation was. Go to the next reminder, by the way, problem 8-20. You don't actually have to do it. So you cross that one off. That was one of the ones I told you not to worry about. The other one is 8-22. I told you that on the back side of the first page there. And the problem I want to go over together real quickly is problem 8-21. I forgot to mention this yesterday. It's been a while since we've done some of these problems, and I just want to, one, revisit how I want you to do them, because it's not what the directions say. And then 2, just we'll do it together just to remind you. So if you take a look at this problem, notice the directions say write an equation for these sequences. We didn't even do that. We didn't cover it in Algebra 1. We didn't even talk about it in this class. So I kind of laugh sometimes, by the way. These problems a lot of times are the dead giveaway of whether people are just copying answers out of the homework help. Because if you have the equations to these, it's like, wow, I wonder where they learned that. Because you're never taught it, but somehow you got the exact answer perfect. Okay? So just a heads up that sometimes a dead giveaway whether people are just straight copying out of the homework help answers. But here's what I want you to do. Ignore those directions completely. Okay. And I mentioned this, but it was a while ago that I mentioned this. Anytime you see these problems that are the sequence of numbers, I want you to do 2 things. Okay. Identify whether it's an arithmetic sequence or a geometric sequence, and then tell me what the corresponding either common difference or common ratio is. So let's revisit that just to refresh your memory. What's the difference between arithmetic versus geometric? How can you tell? What's the difference between those 2 types of sequences? Anybody remember? Lynn?
Isn't arithmetic like adding or subtracting?
Yep.
And then geometric is like multiplying?
Yep. So the difference, that's exactly what it is. An arithmetic sequence is where you've got repeated addition, where you're adding the same thing every time. So even if you're subtracting, you can think of it as you're adding a negative. Okay. A geometric sequence is repeated multiplication. You're multiplying by the same thing every single time. So if we take a look, what does that mean then for part A? Arithmetic or geometric? Based on the pattern. We'll do this together. What do you think? No, what do we got? Okay, why? What's the pattern?
Plus 15.
Yep. This is an arithmetic sequence because we're adding the same thing every time. That what we're adding, if you remember back, is called the common difference. It's the difference between any 2 terms. So down here, I'm going to put D equals 15. There it is. That's all I want you to do for that. Identify arithmetic versus geometric, and then tell me, in this case, the common difference. What are we adding every time? How about part B? Arithmetic or geometric? What do we think? Brady, what do you think? Arithmetic or geometric?
Geometric.
It is geometric. Okay, we're not adding the same thing, because if you notice, we'd be from 9 to 3, we'd be subtracting 6, then we'd be subtracting 2. Well, that's not the same, so it's not arithmetic. So this is geometric. This one's a little bit trickier. Common ratio is what I'm looking for, and the common ratio is what we're multiplying by. What do I multiply 9 by to get 3?
3.
Yeah, it's close. 0.3 repeating. It's 1/3. A lot of times people look at this and they say, oh, you're dividing by 3. And you're right. But when we do a geometric sequence, you got to think of it as what am I multiplying by? And if you remember, anytime you divide by something, that's the same thing as multiplying by the reciprocal. So like dividing by 2 is the same thing as multiplying by 5. Dividing by 3 is the same thing as multiplying by a third. Dividing by 4, multiplying by a fourth, so on and so forth. So your common ratio on that one is 1/3. That's all I want you to do for those. Anytime from here to the end of the school year, if you see these sequence of these number patterns, ignore the directions completely and do that. Okay, that's all I want you, because there's a whole chapter on this that you'll get into next year in either CCRM or Algebra 2. And that's where you'll start to find all the equations and you'll go much more in depth. Okay, so for now, if you can identify that, you were in good shape. Any questions on that? Anything make sense or anything not make sense, I should say? Okay, those were the two from the practice to learn that I wanted to try to address just to make sure that you're understanding some stuff. Like I said, this is due by tomorrow. Okay, so make sure you get that taken care of, get that turned in. All right, let's go to the lesson. Here is your lesson for today. And here's the main idea. You can see I highlighted it. Yesterday we talked about, and you don't have to worry too much about even going, if you want the book in front of you, go ahead and go into the ebook and bring it up. That's perfectly fine. If you don't really care and you just want to look up at the screen, that's perfectly fine too. Okay? So it's totally your preference. So yesterday, the only thing we talked about was how do I find the sum of the angles of pentagons, octagons, decagons, whatever, however many sided shape. Today, we're going to specifically focus on regular polygons. And if you remember the word regular, a regular polygon has all sides being the same, all angles being the same. Okay? Both sides and angles are all congruent to each other. And so if you notice, let me kind of give you a little bit of background information here. And this is not made up. This is not like a made up geometry problem. This book does a good job of getting real information versus just made up numbers and made up problems. Kind of, most of the time they do. This one's for real though. Diamonds are a very valuable, naturally occurring gem. Have been popular for centuries because of their beauty, durability, and ability to reflect a spectrum of light. In 1919, a diamond cutter from Belgium, Marcel Tolkowski, used his knowledge of geometry to design a new shape for a diamond called the round brilliant cut. And they show you off to the side there the top view of the diamond and how they cut it. Okay. He discovered that when diamonds are carefully cut with flat surfaces called facets or faces, in this design, the angles maximize the brilliance and reflective quality of the gem. Okay, so that's the idea. They find some diamond and then they go through and they cut it at different angles, and all the different cuts are what make a diamond shine and make it what it is. And so part of that comes into, there's some geometry to that to make sure that it shines at kind of the maximum amount. So if you notice, at the center of this design is a regular octagon with equal sides and equal interior angles. For a diamond cut in this design to achieve its maximum value, the octagon must be cut carefully and accurately. One miscalculation and the value of the diamond can be cut in half. So obviously it's important to get it right. So here's what I want you to do. I'm going to give you about 3 minutes probably, I think is all you'll need. If you take a look at parts A and B, I want you to use what you know from yesterday to determine the measure of each interior angle of that regular octagon. And then I also want you to do part B. Find each interior angle of a regular nonagon. Remember, that's a 9-sided shape. And find each interior angle of a regular 100gon. Okay? Starting though with the octagon, think about what you already know from yesterday and try to apply it to that. Okay? I'm going to give you 3 minutes. See what you can come up with. Let's go to work. You can just, if you want to just flip the warm-up over, the whole backside of the warm-up is blank, so you can just do it right on that. All right, let's go to work, see what you can come up with. Each interior angle. Also, do me a favor, take the practice to learn and put it away. Because I want you to focus on the lesson. If you can find this is 813. Each interior angle. You can come up. Discuss it. Again, I encourage you to discuss it.
I'm stupid.
We're doing, we're doing anything that we're supposed to be doing? One day, not allowed, nope. Trying to find the sum of the 8 points. For the next 6 days.
I'm saying you're trying to.
One actually literally.
Each one of those 6 days. One of these 6 days.
Yeah.
There. Just draw on it. Start with the sum. If you're stuck, start with the sum of those 8 angles of your regular octagon. And then try to figure out what you do from there. You can figure this out. I know you can. Yeah, you were right. Good. So there you go. You got the idea from yesterday. Yeah. Sure. No, it's hard to write. Just divide it.
Sorry, and it's stopped.
How many angles is that? So 10 divided by 8, or by 8.
All right, let's take a look. See what you came up with. What'd you get for, somebody help me out on part A, octagon. What is each one of those interior angles equal? 135, okay. What'd you do, Lennon? How'd you get?
It's the 180 times 8 minus 2, and I got 1080 and then divided it by.
Okay, yeah, the idea here is, as you work your way through this, find the sum of all of the angles, which in this case for an octagon is 1080. That's what we did yesterday. And then, because this is a regular octagon, we know that all 8 of those angles are going to be the same. So we can take that sum and divide it equally amongst all 8. You end up with 135 degrees. Okay, how about in part B? How about a nonagon? What'd you get for each angle? Parker, what'd you get?
For the nonagon, I got 140 degrees.
Okay. And what did you do to get that?
I did the sum equation, so like
Yep.
180.
Okay.
And then I got 1260, and then I divided that by the 9 together.
So you did the same process to get it. Okay. How about a 100 gun? Ready?
176.4.
Yep. Should end up with 176.4. And I think I know the answer to this, but I'm going to ask it anyway. Do the same thing.
Yep.
Okay. So the process, all you're doing in this case is to go through, find the total, and then divide it equally amongst however many angles you have. Now, let me ask you this question. Will that work for any polygon?
Yes.
Will work for any regular,
Somebody said, there it is. Matthew, what'd you say?
will work for any regular, but not any polygon.
Why will it only work for regular polygons, but not any polygon?
Regular.
Help me out. Let's go, let's elaborate a little more than Connor did. You're right, though. Yeah, all equal sides and all equal angles. And so therefore, because of if the angles are not all the same, well, then I can't divide it equally amongst all the angles. We have to go through and we can only do that if we know the angles are all equal to each other. So ultimately, you don't put this on your toolkit yet. We'll do this at the end. But the idea is we're taking the sum of all the angles. That's this 180 n minus 2. That gives me the sum. And then we're dividing it by what? Yeah, however many sides you have, which is how many angles. You're just dividing it equally amongst all of those things. So that's really all we're doing. It's taking that concept. Okay, let's go to the next problem here. This one we're going to do together and just kind of discuss. And we discussed it a little bit here already. But Fern states that if a triangle is equilateral, then all the angles have equal measure and it must be regular. Okay, true statement? Equilateral triangle have all equal angles. Okay, and if you got equal angles and equal sides, you know it's regular. Okay, so that is a true statement. The question is on that one, is that always true? You take a look at part A. If you know all sides of a polygon, like a quadrilateral, are equal, does that mean that all the angles are equal and therefore it's regular? What do you think? Think about the quadrilaterals. If you know that all the sides are the same, does that mean that all the angles have to be?
Yeah.
I see yes and no. Alex, you say no, what? Why not? Give me an example. There's your example. So right here it says draw a counter example. I'm not going to draw it, but there's your counter example right there. A rhombus has all equal sides, but does not have all equal angles. Okay? So just because you know the sides are congruent, that does not necessarily mean the angles are, and therefore it doesn't necessarily mean it's regular. How about in part B? What if you know the angles are congruent? Does that mean the sides have to be? Why not, Brady? Give me an example.
Rectangle.
Like a rectangle. Rectangle's got 4 90-degree angles. It does not have 4 congruent sides. Okay. So the point that this problem is trying to get at is trying to get you to recognize that if for something to be regular, you got to be careful. Sides don't always mean angles are congruent. Angles don't always mean sides are congruent. And in order for it to be regular, you have to have both. Okay. So just be careful on that as we move forward. Okay. All right. Here's the next thing we're going to get into. Now we're going to transition. We focused on some of the interior and each interior. Now we're going to exterior angles instead. We're going to take a look on the outside here. So if you notice in part A, it says examine the regular hexagon. So in this one, they're telling you it's a regular hexagon. Angle A is an example of an exterior angle because it's formed on the outside of a hexagon by extending one of the sides. So if you notice in this shape, if I take this, there's one side of a hexagon, and if I just keep it going, it ends up creating an angle on the outside, in this case, angle A. And what I want you to do, and they ask, are all of the exterior angles of a regular polygon equal? I mean, think about that for a second. What do you think? Intuition, are all these 6 angles right here, are those all equal in a regular polygon? Yes? Why? Give me some reasoning. Give me some reasoning as to why they are. How do you know? Without doing any work. Right, by the way, they are. Not sure? Right? Exactly. If you think back to, again, if we go from interior to exterior, if you can figure out, let me switch colors here. If I could figure out that angle, I know these 6 have to be equal, right? And therefore, if those 6 are all equal, well, the ones right outside, they're supplementary. They're going to be the same amount is going to be the exterior angle. Okay, so we know all 6 of those are going to be equal to each other. So here's the question I have for you. Here's what I want you to do. This one I'm only going to give you about a minute or so because I don't think it'll take much longer than that. I want you to find each interior angle of that regular hexagon. Then I want you to find the corresponding exterior angle, angle A, and then find the sum of all 6 of those angles. Okay? Interior angle, corresponding exterior angle, and the sum of all 6. I'll give you it shouldn't take you more than about a minute or so to do that. Okay? Let's go to work. See what you can do, and I'll call on somebody to answer.
I need to pull up.
Where's this one? So the interior?
Is this able?
No, don't worry about this. I mean, you need this sum in order to get each one, but find each interior, each exterior, and then sum of the exterior. Bam. Bam. All right. Let's start with the interior. What are the green angles all equal? Each one, so a total of 720. which means each one we divide by 6. Each one of these angles is 120 degrees. Okay, therefore, what's the measure of each exterior angle? Bailey? What is it? 60 degrees. Because those are supplementary to each other, the interior and the exterior angles. Which then, if we take it one step further, what's the sum of all 6 of those angles?
360.
360 degrees. Okay, the sum of all 6 of those exterior angles. Here's what I want you to do now. Here's the next thing. Now the question is, that's a hexagon. Let's look a little bit closer at 4 other shapes. And I'm going to split this up. I'm going to have you just do one shape. So what I want you to do is the same idea. Row number 1 here. I want you to do part number 1. Equilateral triangle. I want you to find each interior angle, the corresponding exterior, and the sum of the exterior. Those 3 things. Okay? Each interior, exterior, and then sum of the exterior. Row number 2, I want you to do the irregular octagon. Find each interior angle of an octagon, the corresponding exterior, and the sum of the exterior. Row 3, I want you to do a regular decagon. And my back row, I want you guys to do a regular dodecagon. Okay? The interior, exterior, sum of the exterior. Those angles. And then we're going to discuss, and I'll randomly call on one person from each row to give me the answers. See what you got. Again, I'll give you a minute or 2 here to find the answers. What are we doing? Are we ready yet? Not yet? Okay, I'll give you another minute or so. Interior angle. The corresponding exterior angle. And then the sum of the exterior angle. So those 3 things.
Wait. When I was in California, Goes where? Goes over.
This is good.
Yeah, clear.
That's good. That's good. Here, we go through. 100%. Just extend the side. So you just take one of these sides and just extend it. Like that.
Oh. Would you find by one to count it? Or have a chance to miss it?
Good question. All right, let's take a look. Let's see. Row number 1, as we do equilateral, what'd you find? Ready? Go ahead. What'd you find? What was each interior angle?
60.
Okay, so we got 60 degrees for each interior. 180 total for a triangle, divided equally by 3. How about exterior?
120.
Corresponding angles 120. And how about the sum of the exterior?
Some exterior would be 360.
360. Okay, so there's our first answer. All right, row number 2. Hunter, I'm going to come to you. What was each interior angle of your octagon?
I got 108.
Doesn't see somebody else get the same answer. Oh, what'd you get?
35.
I think that's right. I think it's 135. Granted, I'm going off the top of my head, but I think it's 135. Okay. How'd you get it, by the way, since we made a mistake? What'd you do?
Since it's 8 sides, I did 8 minus 2, and then I multiplied that by 180.
Okay. Yeah, same.
The wrong amount of size.
There you go. That'll do it. So we got 135 for each one. So I'm going to come back to you then. So therefore, what's the exterior?
45.
Okay, 45 degree for each exterior. And how about the sum of all the exterior? 360. Okay. Let's go to a regular decagon. Let's go row 3. Harry, I'm coming to you. Regular decagon. What was each interior angle? Yeah, I think that's right. That sounds right. And rest of the row? Yeah. 144, oops, so therefore, what about each exterior angle? A little too big, I think. 36, yeah, that sounds right. 36 should be good. And sum of all the exterior angles? 360, okay? Ah, patterns. How about a regular dodecagon? So last row, let's go. Kara, let me come to you. What'd you get for each angle of a dodecagon? Okay, yep. Exterior. And sum. Good. All right, let's look at some patterns. Hands go up immediately. All right, Adele, what do we got?
They all have 360 degrees.
Some of the exterior angles, some of the exterior angles, some of the exterior angles, some of the exterior angles. Let me ask you a question. What do you think the sum of the exterior angles of any polygon are? 360. Doesn't matter the number of sides. It's always 360 degrees. Okay, what else, Lana?
Two angles always add up to 180.
60 plus 120, 180. 135 plus 45, 180. 150 and 30, 180. 144 and 36, 180. Okay, so we do have quite a few parts that we can talk about with that. Now, one final thing, and then we're going to go to the toolkit. And that final question that I have, this was all regular polygons. What if it wasn't a regular polygon? We said 360 degrees. What if it's not a regular? Like, take a look at the quadrilateral. That is not a regular quadrilateral. That is not a square. You think it still holds? You think we're still going to end up with 360?
Yep.
Okay, let's find out. Let's make up some numbers. Let's approximate angle measures here. This one looks like it's approximately 90, so let's call it 90, which means the exterior one has to be 90. Okay, there's one exterior. This one looks bigger than 90, let's call it 100, which means the exterior one has to be 80, supplemented. Let's come down here. Let's call this one looks a little less than 90. Let's call that 80. Therefore, this one's got to be 100. There's your third angle. And then what's left in our quadrilateral here? The interior does. And that's what I'm doing right now. That's what I got to figure out what that last one has to equal. 170, 270, so that's the 90 again. Yeah. So this one's, even though it's not 90, it's approximately 90. And therefore, exterior is 90. What do those circled numbers add up to? 60. What do we get, Steve? We end up with 360 degrees, just like we did with the regular shapes. Okay, so the point we're trying to make is not only is the sum of the exterior angles 360 with a regular shape, doesn't matter whether it's regular or not. Some of the exterior angles 360 degrees always. Okay, all right. Let's go to the toolkit. Let's summarize some stuff here. So take out your green toolkit. We're gonna add what we figured out. So there's the next box on the toolkit. We had already filled out yesterday the upper left hand, the sum of the interior angles of any polygon. That's how we find it. Now we just said the sum of the exterior angles of any polygon, 360 degrees. Matter how many sides, matter whether it's regular, not regular, doesn't matter. Sum of the exterior is always 360. So if you notice, I did not just throw these in random boxes. I tried to organize the boxes as well. Left-hand side, we're talking about interior angles. Right-hand side, we're talking about exterior angles. So then if we go through to the next part, we then said, on the left-hand side, if I wanted to find each interior angle, you take the sum of all the interior angles and divide it equally. That's what that formula says. 180 times n minus 2 is the sum. Divided by n, divided equally amongst all the angles. We didn't talk about each exterior, but it should make some sense. Take the sum, 360, and divide it equally amongst all the exterior angles. to find each angle, it's always the sum divided by however many you have. And one thing I want to make you aware of as well, and I kind of, if you notice on each of the titles, I put some words in bold, I put some in just all caps, okay, because those are kind of the key things that we're taking a look at. Again, each interior on the left, each exterior on the right. Key part though, these formulas only work with regular polygons. Okay, because of that fact that unless they're all equal, I can't divide that sum equally. That only works if it's a regular polygon. That's why I put the word regular in all caps. And then finally, last bit of things that we're talking about. We've got every interior angle that you find and the corresponding exterior angle are always supplementary. Interior angle plus the corresponding exterior angle will always equal 180. And where we're then headed into the next section is nothing new. What it is it's going to basically say they're going to give you some information, and then you need to go through and take that information and kind of find the other parts. If I tell you how many sides, you should be able to tell me the sum. You should be able to tell me the each interior, each exterior, all that kind of stuff. Okay, they're all related to each other. And so the last thing that I have for you today, where we're at, we're not quite done, but we also don't have enough time to finish it. So I'm gonna kind of stop at this point. We will kind of wrap things up on Monday. By the way, I don't know if you noticed, I did totally different note. I did put your grades for your tests in Canvas yesterday. So those are in there. I will probably hand those tests back on Monday, just so you can at least see where you made your mistakes. But the grades are in Canvas. Here is where you're at in terms of assignments. 812, like I said, due tomorrow. Start working on the 813. Okay. We're going to continue 813 on Monday and kind of wrap that up. And there's your first Delta Math assignment as well. What I would suggest, because I'm not going to let you go for about another 8 minutes yet, until about quarter after. What I would suggest is either work on some of the homework problems, or go into Delta Math and start working on some of those Delta Math problems. See if you can get that done. That's that for today. Okay. Get a few problems done over the next 8 minutes before we go.